Welcome to 122 Live, and we are going to go ahead and finish off our discussion with Chapter 10. So let's go ahead and look at where we left off. So before we talked about D flip-flops and we talked about SR flip-flops and what those look like, and we can construct them from cross-coupled NANDs and cross-coupled NORs. And so we're going to take the idea of the SR flip-flop and use it in a little bit different way that will ultimately allow us to create counters. Okay, so this is a very important thing that was figured out to get us into a toggle mode where we can always just always go between 0 and 1 and 0 and 1. Okay, so that's where most of the JK flip-flop stuff is used. And so we orient them in what we call like a master-slave orientation. And so you may be familiar with how computers are constructed, and so it works off the same principle where you have a main hard drive, your master hard drive, and then you can have slave drives that depend on that aren't the main source. It's kind of like your C drive, right? Your C drive would be sort of like the master, and then you could have other drives off of that. Okay, so typically what we use the JK flip-flop for is this, what we call the toggle mode. Now, this is a new mode that we haven't talked about yet. When we were discussing SR flip-flops, they have three modes, right? They've got the 0-0 condition where things remain unchanged, so that's what we call the hold condition. Then you could also have a 0-1 where set is 0 and reset is 1, and that's what we call the reset condition, and the output goes to 0. And then if you have the 1-0 condition where set is 1 and reset is 0, that is called the set condition. So if you are in one of those three conditions, you know how the output reacts. And we said that with the SR flip-flop, that if you do have a 1-1 on the output, that actually pulls both of the Q0 outputs low. Okay, and so that's what we call the unused condition. So what the master-slave JK flip-flop does is it allows a pair of SR flip-flops to work together, and because of how we can cross-couple back to the beginning AND gates, we can have a fourth condition where we use that 1-1. Okay, and so now when we have a 1-1, Q is toggled. That means if it was a 0, it becomes a 1. If it was a 1, it becomes a 0. And so if we're going to start counting in binary, that becomes a very, very useful thing. Okay? So the front SR flip-flop receives the data while the input trigger is high, and the second set are off during that period. And then while the input trigger is low, the master SR flip-flop turns off, the slave turns on and accepts that information and then outputs it. Okay? So here we go. Like it says here, J kind of acts like set and K acts like reset. So we kind of think about SR because they're going into two SR flip-flops anyway. On the next slide, we'll show that. So anyway, this 1-1 condition now becomes the toggle condition. Okay, so it depends on what Q was. So it just becomes the opposite of whatever it was before. Okay. So here you go. So here is the master SR flip-flop with a pair of AND gates in front of it, and then a slave flip-flop, SR flip-flop, with the two AND gates in front of it. Okay, and so this outer box here, I love the way Kleitz does this because it's very well constructed, and it's very easy to see how this stuff is set up inside the box. So this outer rectangle here, think about that like the IC chip edges. Now there's more of these in here than just this one. But think about it in terms of this box right here. So this is the symbol that we use and what it looks like in Quartus when we use a JK flip-flop. It's going to have a J and a K. The ones that we use, I believe, also have an asynchronous set and reset, which we'll talk about those as well. But anyway, there's a J and there's a K, and there's also what we call the clock pulse, or C sub P. So the clock pulse comes into the first set of these AND gates here. And so while CP is high, remember we talked about enabling and disabling signals in 112. So we're enabling, right, when you've got AND gates that are acting like a gate, like an actual gate out here, and you have a high on one of those inputs, it enables the other two. So if you have a 1, 1 here, those ones get passed on to the SR, okay? If you have a 0, 1, that, this one will still have a 0 because it'll have 0, 1 on the input, so that'll still give you a 0. And this one will be a 1, 1, which will produce a 1. So essentially what you're doing when you enable one of these two terminals, one terminal on each one of these gates with a high, you're passing through J and K. So those pass through onto this SR flip-flop. That's going to change this Q. And so now these Qs have been changed on the inputs over here. But remember, while this is high, if it makes its way through this inverter, right now it's low in the first part of this. So these are always going to be in a hold condition, or at least for the first part of this, because if you have 0 and 0 on here, then it doesn't matter what Q and Q naught are, because it's just going to give you a 0, 0 out, and so you're in a hold condition right here. So for the first half of this, while this is high, this is in a hold. So 1 and 2 are enabled first, then clock pulse goes from high to low, and now these two are turned off because you have a low on the inputs of each one, so those go into a hold, and then now that 0 goes through the inverter and becomes a high, and it enables 3 and 4. So 1 and 2 enabled first, and then 3 and 4 passes it, and then you get a change on Q. So here's the thing that happens though. If your clock pulse is at, let's say, 10 kilohertz, it's taking the front half of the cycle to load the master, and then the second half of the cycle to load the slave, and then get a change on the output. So if your clock pulse, if this was in toggle mode, let's say it was a 1, 1 here, so Q is just going back and forth between 1 and 0. And if you have a clock input, a periodic square wave input, let's say, what it'll do is it'll take the frequency and halve it, H-A-L-V-E, halve it. So if it's 10K on the input, you're going to get 5K on the output, okay? So essentially the frequency of the output is always half of whatever the clock pulse is, or whatever the source frequency is, okay? So that's the generic operation, okay? Basically you just have one that feeds into another. Where this picks up its toggle mode is, you'll see here, I haven't focused on it yet, but you see this dotted line that goes from Q naught, the very last Q naught, and feeds back into this first one. And this Q feeds back in over here to the K. So these are actually 3 input gates. Does everybody see that? 3 input and gates. Okay? So that's what enables the toggle operation. Right. So here again, the enable disable operation of the CP line, and this is reiterating what I'm talking about here when I'm talking about this line being high and low. So while it's high, gates 1 and 2 is enabled and the master is loaded. Then it goes low, gates 1 and 2 are disabled, and now 3 and 4 are enabled. And that's when the slave gets loaded from the master, and then the output will change, and then the cycle repeats. So 1 and 2, and then 3 and 4, and then 1 and 2, and 3 and 4. But you can see it takes that entire clock pulse there to do that one operation. So that's why the frequency is always half. So if that clock pulse is what we call pulse triggered or level triggered, which you may or may not see on a quiz, that is, the input data is going to be read the entire time that the clock pulse is at a high level. Okay, so here's a problem with that, is we have what's called a ones catching error. If you have this situation here where the clock pulse is supposed to be low, what happens if you get a spike on here and that TTL or CMOS chip accepts it as a high? You could have a voltage spike that's high enough on the line that tricks it into thinking it's a high, so it's going to go ahead and transfer to the next cycle. It's going to load the gates 1 and 2, and now you've got a glitch in your program. Okay, so that's the problem with just having a pulse triggered JK flip-flop, or level triggered. In other words, the entire time this is high, that's going to be accepted into the gate. Okay, and then if you have, like I said, if you have a low here, it's supposed to be low the whole time. You could have a brief intermittent noise on the line, and then it's going to register as a high. Okay? So, like you see here, it says eliminated by newer designs using edge triggering, and that's what we will use the entire semester is edge triggering. So an edge triggered JK flip-flop, the way you can tell the difference is, I said here is what we'll use in Cordis, right? So this is back a few slides with just the JK on here. This is a pulse triggered or a level triggered JK flip-flop, okay? Because I don't see the little arrow here, the little triangle. So this is an edge triggered. I know it's edge triggered because I see that little triangle where you see my mouse here, okay? And if it's positive edge triggered, in other words, it's looking for the transition from the clock pulse from low to high, only that point in time right there is J and K accepted in, okay? Now, to further make sure that there's no noise on the line, you really want to use a negative edge triggered JK flip-flop because you're looking for the moment in time where it goes from high to low, okay? So, as opposed to while the entire clock pulse is high, that entire time it can take on, those little spikes accidentally and register those as a high. You only accept the data on J and K when there's a negative edge. In other words, the clock's transitioning from high to low, or the clock's transitioning from low to high. Okay, so it doesn't get sampled as often, but it prevents some of that noise from getting on the line and causing a disruption in how it operates. Okay, so here's the function table that we would use. This is for a negative edge triggered, and I'm saying that because, number one, it's the CP here with the bar over the top. That's how we typically will signify the difference between the two, right? So the bar means negative edge triggered, and this, if you just see regular CP, that's just positive edge triggered. So anyway, I know that this is, when the clock pulse goes from high to low, and I have these conditions here on J and K, here's how the flip-flop will operate. So no difference between the SR and the JK from, 001001, but this new condition here is the 11 condition, and so whatever Q was before, it becomes the opposite. Whatever Q not was before, it becomes the opposite. Okay. So I think Kleitz does a really nice job of laying how these operate out. So there's what kind of what it would look like in Cordis, and so some of you may remember this from 112. So here, we have a clock pulse in here, and to make it negative edge triggered in Cordis, I believe it's still this way. You have to put a NOT gate in front of there. That way, it produces this inversion right here. So anyway, we're going to have a lab that details this that I will have posted later. Okay. So just to reiterate, how our pulse triggered or level triggered device is different than edge triggered. Pulse triggered accepts the inputs the entire time that it's high, and you could run into a situation where you have a ones catching error where the entire time it's low. It's possible that it could have a brief high, and it will accept that as a high, and it will cause your flip-flop to toggle early. And that's what the ones catching is. And it says identify the synchronous and asynchronous inputs. Well, okay, there we go. So I don't think there is one on the one that we looked at here. Nope, this does not have the asynchronous inputs on it. So let's look at one. This is actually from one of the IC chips. So 7476 is what you could also use. If you type in the 7476 in Cordis, they have a chip that you can use that mimics this, okay? And so here we've got, this is, the 7476 is positive pulse triggered, and the 74LS76 is the negative edge triggered, this is the one that you want. But I don't remember I can't remember if Cordis has the LS in it or not, okay? They might have it in the new Prime version. I can't remember. But anyway, so we know what J and K are, right? And we know what Q and Q not are. And we know what the clock pulse is now, right? Now I know this is negative edge triggered. I know it's edge triggered because of the triangle, and I know it's negative edge triggered because of the bubble in front, the inversion right here. The other two are the asynchronous set and the asynchronous reset. Okay, these are both low. So they kind of work the same way as the negative edge trigger here, right? If you want to make these unusable, then you would tie them both high because they're active low inputs. So, if you wanted to reset this flip-flop to 0, to where, Q would go to 0 and Q naught would go to 1, you would have to put a low on this input. Okay? And so at rest, you really want this thing to be high so that it doesn't accidentally reset your flip-flop. On the other side, if you want to make the output 1, 0, then you use the asynchronous set. Okay? So these two override anything that's happening on the synchronous inputs. If you ever see a question where it says, what are the synchronous inputs of a flip-flop? Then you would say J and K and CP, right? And then you say, what would be the asynchronous inputs? And that would be the asynchronous set and reset. Those take precedent no matter what's going on in the circuit. They will override, even if it's on the negative edge trigger. If this is a high or if this is a low or if this is a low, then it has control of Q. Right? So those take precedent no matter what. And that's why they're called asynchronous, because they can change the output at any point in time. The synchronous inputs can only change the output, in this case, on the negative edge of the clock. Okay. And if you have a JK flip-flop and you need to make a D flip-flop, there is a D flip-flop in Quartus, DFF. The JK, the generic one, is JKFF, if you're searching for them. Here it says connect unused asynchronous inputs to 1 because they're active low. And so if you want to make them unused, then you tie them both high. And if you remember in Quartus, that's VCC if you type that in. Okay? So here we have one single data input, and then to make it a D flip-flop, remember you have to put an inverter before, we talked about S and R before, but J and K, same thing, right? For all intents and purposes. So D will come in through here, and then D naught will be here. So you only ever have either 1, 0 or 0, 1. A D flip-flop will never go into toggle mode, and it will also never go into hold mode. It's always in set or reset. Those are the only two conditions, okay? So I think that may be it. I don't want to talk about the LPM. So let's just recap all of Chapter 10 here. So we talked about the SR flip-flop. Being a way that we can now store a bit of information, and we can construct it using basic gates. We could use the cross-coupled NOR scheme, which just requires 2 NOR gates, or we have the cross-coupled NAND scheme, which requires 2 NANDs and 2 inverters. Enabling gate circuitry, or adding gate-enabled circuitry to the SR flip-flop makes it synchronous. All synchronous means is something else is controlling it, so that could be you pushing a push button to enable it. It could be some other sensor going high doing it. It could be just a clock that runs all the time. Okay? So, or some other enable signal. Just something else is controlling how it operates. Okay? D flip-flop only has a single data input and is only ever in reset or set. So we talked a little bit about the 7474 and the 74LS76. And so the JK flip-flop differs because we can use that 1-1 condition to perform a toggle operation, and toggling means that Q flips to its opposite state. And the master SR, slave SR setup consists of 2 latches, one that receives the data while the clock is high, and another that receives it while it is low. And there we go, the 74LS76, edge triggered, negative edge triggered. That's what we would be using if we were building these in class. Okay, so that is all of the rest of Chapter 10. Okay, so let's go ahead and dive right into Chapter 11. Okay, so we are going to peek a little bit further into these transition points. I told you, if you had me in 112, I told you we were going to get down into the weeds of, how this stuff operates, down in the nanosecond region, right? So you may have noticed this in Quartus before, and if you had me in 112, I point this out, okay? Because what happens if, when we get into Quartus, it has these nice crisp edges, And things are allowed to change at the same time when you do the functional simulation, just to see how it works. When you run the timing simulation, it actually takes into account propagation delay and things like that. So what do you do if, this is a negative edge triggered flip-flop, right? And so we are waiting to make sure the clock is transitioning from high to low. And at this one point in time here, J and K are being accepted on the input. Now, K is 0, okay? So really the only condition here is either, a hold or a set. That's it, because you can either have 0, 0 or 0, 1. So initially it has an asynchronous reset that pulls at 0. You can see that here. And so that's why output at Q is 0 here. It has an initial state. Okay, now when this clock pulse goes from high to low at this one point in time, at the same time, J is transitioning from low to high. So does it accept J as a low or does it accept it as a high? I don't know. So when you have something that exists like this, we call that a race condition. Okay? And that just means that you have multiple things transitioning on a clock edge. And so unless you run your simulation a lot of times and try to do it in real time, you really don't know how Q is going to operate. Maybe it accepts it as a 1, maybe it doesn't. Maybe it remains at, maybe it didn't transition fast enough and it read it as a 0, 0 and kept it in a hold. Or maybe it did transition quick enough and you now have a set. That's why you see both sets of lines here. You see the set line and then also keeping the reset line. And so when it does actually transition, so that we don't have this race condition, right before it transition, it has to be stable, okay? And so it says data manual provides AC waveforms to illustrate measuring points. You have to make sure that you have a setup time that's honored, all right? So essentially, it kind of sounds like it's doing time travel, but it's not. It says how far back the flip-flop looks to determine input levels, okay? So it needs to be stable before the clock pulse goes from high to low, right? So here you see it right here. So here's the transition of the clock pulse from high to low at this VM spot right here, okay? That's where it triggers. And so before it, and this could be 3 nanoseconds, it could be 5 nanoseconds, it just depends on what the data sheet for that chip says. But there's some period of time where it has to be stable, back up here, so J and K can transition all at once, but at this point in time, right here, that's what it's going to accept as if it's a low or a high, okay? And sometimes the setup times are different. You may have one for if it's going from high to low or low to high. But anyway, it looks back every time you have a trigger point here of high to low for your clock, or low to high, whatever it is. This one is a high to low. So those are my trigger points. And so, in both cases, it looks back to see what the output or J and K are. Okay? So the setup time is how far back it looks to determine what the input level is. Should I accept it as a high or a low? It has to be stable. Okay? And like I said, it's typically a couple of nanoseconds, a few nanoseconds. Okay? The hold time is what happens after that trigger point happens. So you can see here, not only does it need to be stable before, but in most cases, or in some cases, it needs to be stable afterwards as well. So not only should it be stable just before the trigger happens, it should also be stable just after. So really, there's a little sliver range of time where you don't want things to be changing, or the flip-flop is going to operate under race conditions, and you won't know how it operates all the time. So in this case, we've got more than that. So the setup time here is 20 nanoseconds. Okay, so it wants stability for 20 nanoseconds before this thing transitions, so it locks in the low. Right now, on this particular device, I don't know which one this is. It doesn't tell us, but whatever device we have here, the hold time is 0 nanoseconds, and that's why I caught myself a little while ago and said, in some cases. Some chips do have a hold time. A lot of them, however, do not. Okay, so they've advanced the technology to where It just needs to be stable before the trigger happens and not necessarily afterwards. If it's set up beforehand, then it's fine. Okay? So I just wanted to point that out, that sometimes the hold is a 0 nanosecond hold. Just depends on what the data sheet says. So here we go. We talked also about propagation delay. We're getting into the nuances of what happens when you have this transition from a high to low, or what happens when the clock pulse triggers. What actually happens when it accepts those inputs? Okay, this says when you make a change on J or K, and you change and that change affects a change on Q, how long does it take to get from J and K to where you have a Q that's changed? That's the propagation delay, the time from the input to the output. How long does that transition take? You've got the two SR flip-flops inside of there, and so it takes time to get through all those gates and to get through the other flip-flops. Okay? So that's always on the data sheet, and it's typically different when the output is going from a low to high versus when the output is going from a high to a low when it transitions. So you can see down here the difference between the two. So for this chip, for the 74LS76, which is the negative edge triggered JK flip-flop, if you are changing Q from high to low, it takes 30 nanoseconds. So it takes a little bit longer to discharge and get down to 0 than it does to charge up, okay? Because to charge up from low to high only takes 20 nanoseconds. So on average, and that's the way that we look at this, on average, it's going to take about 25 nanoseconds for this chip for the propagation delay, right? Because one of them's 30 nanoseconds and one of them's 20. So, again, there's going to be some maximum frequency that you can't exceed. So you can't just have, 400 gigahertz, pulsing through this little IC chip. There's some maximum frequency of, at which point it does not operate like it's supposed to. Probably because you're violating the setup time, right? If it changes quicker than 20 nanoseconds, then you're never going to be able to use that chip because the setup time is 20 nanoseconds. So what if your period was 5 nanoseconds or 10 nanoseconds? That's way too quick for one of those chips. It'll tell you what the clock pulse width is, and some other things on there. But really just I wanted to point out the maximum frequency. Okay, because maximum frequency will become something we talk about in chapter 12. All right. And I believe the last thing I want to talk about is an automatic reset. Okay, so this one I have asked for on on exams before, to where I say, hook up, a J and a K and make this thing have an automatic reset. So in other words, when you turn the power switch on here, this thing is going to put an asynchronous reset on both of the JK flip-flops on this one chip, because there's two of them. So it's going to put an asynchronous reset on both Qs, Q1 and Q0, and well, I guess it's Q1 and Q2 here. So it's going to put a 0 on each one of those to initialize it, right? And it does that with an RC circuit. So I'm pretty sure all of you have taken 111 at this point, and so you would have covered RC circuits at some point, right? And with me, it's in the last third of the class, chapter 13. So what happened when we talked about RC circuits? When you initially throw the switch, what happens to the voltage? All of it goes to the resistor initially, okay? And the capacitor acts like a what? Right? Whatever voltage it was at before, it wants to stay there. So it shoves all the voltage onto the resistor, and it can remain at 0 volts. And if it remains at 0 volts, that means essentially these are attached to ground. So you have a low that's initially on the reset here. So as that, after that switch is thrown, you put that initial 0 on here, what happens to the capacitor over time? It charges, right? It'll charge up to this 5 volts. How long does that take? Well, it takes 5 time constants, and if you remember from 111, that you take 1K times the essentially 1 nano, and you would come up with what? 1 microsecond. Okay, so after 5 microseconds, which is very, very quick, right? No, I'm sorry. That's right. 1 microsecond. So, after 5 microseconds, that would be back at 5 volts. So it starts off with an initial 0 because of how an RC circuit works. And then over 5 time constants, this will charge to 5 volts, and then you would have a high connected here, okay? Because all the voltage would be on the cap, and none of it would be on the resistor, okay? So you essentially be connected right directly back here to the 5 volt supply. So that's putting an automatic reset. So you turn the power switch on, it automatically resets the Q1 and Q2 because of the operation that I just described here. Okay, and then you can see the diagram down here about how that works. So here's the switch closed, and it just immediately turns the voltage on. So you have a spike, right, from 0 to 5 volts. So this thing is at 0, 0, 0, 0, and then it gets turned on and it charges high, and then when you turn it off, right, it's going to discharge that capacitor and go back low. So initially it's going to start out low again because this is connected to ground. It's got somewhere to go. Okay? Any questions? I've kind of been paying attention here. Not a whole lot to ask about. It's pretty straightforward. Again, we just recapped how JK flip-flops work, and we talked about how you would do that for a D, how we use a JK flip-flop to make a D flip-flop, and the operation internal to the JK to give us that toggle operation. We talked about race conditions. We talked about ones catching, potentially, and that's why the negative edge triggered, I think, is superior. And we also talked about, in Chapter 11 here, what is the difference between setup time and then also hold time. And so those have to be, you can't violate those, or the flip-flop is going to operate in an unconventional manner, and you won't be able to predict its operation, which is bad news, right? We also talked about propagation delay, how long it takes for the input to change the output going through all the internal gates. And we also talked about the automatic reset. Okay? So, question here. We only have some of those on the board. So if you're talking about Quartus, there are some of these that are that you can do this with. Okay, so I know there's a 7476. I don't know if there's a 74LS76. I'll have to go back and check. But even so, you could just take a generic JKFF. That's what it's called in Quartus, and just use a JKFF or a DFF if you want to. Okay? All right. So if no other questions, make sure you email your professor if you have any questions. And next time we will start in with Schmidt. Okay? See you all later.